Hello again, Chem 1110 students. We're going to talk a little bit more about how molecules are put together and how we investigate it and think about it by looking at electronegativity and polarity of molecules. So one of the things we have to realize is that we talk about covalent bonds. We just talked about doing Lewis structures of those, and that's where atoms actually share electrons so that they see an octet. The kind of molecules we talked about before were ones that had ionic bonds between a metal and a nonmetal, and they're held together by electrostatic interaction. And there is a third kind, and that is sort of between covalent and ionic, and those are called polar bonds. In polar covalent bonds, the electrons are shared but not equally. Okay, so covalent bonds, the electrons are shared equally. And so often when we are going to show this in a slide in text, we put a little delta, that's a lowercase Greek letter, to note a partial charge on the atoms. Like the electrons are spending more time closer to one of the atoms or the nucleus of an atom than the other. And so we have some examples here. A pure covalent bond where we have equally shared electrons. A polar covalent is that the electrons are not shared equally, and therefore we have some partial charges. And then, of course, an ionic bond where we have true charges, a positive and a negative, and they're held together by electrostatic attraction. So on this slide, I have some electron density maps that show the distribution of charge. So if electrons are spending a lot of their time in one place, it's indicated in red. Very little time is indicated in blue. So we have a nonpolar covalent, two hydrogens sharing two electrons. It's as equal as you can get. And so you see that most of the time the electrons are between the two nuclei. It makes sense. They're held there by the protons. And that's where the nucleus wants to see that it has a full 1s orbital. HF is a polar covalent compound, and so in this case we can see that the electrons in the red are spending most of their time on the same side as the fluorine, much less over in the area of the hydrogen. And then we have NaF, sodium fluoride, which is an ionic compound. Sodium gives up its electron to the fluoride, and therefore the electron's not spending any time on the sodium, almost all its time around the fluorine. So electronegativity is what goes along with polarity. It's the ability of an atom in a compound to draw electrons to itself. Remember, they're shared, just not equally shared. And this is a nice graphic of this effect of electronegativity on the periodic table. The higher the column, the stronger. So you see that fluorine has a very high electronegativity. And it is also a very small atom. As you go down the group to chlorine, bromine, iodine, you see that the electronegativity drops off. The same as when you go across that period, fluorine is the highest, then oxygen, then nitrogen, then carbon. And of course, we have the metalloids shown in yellow, but they still have some electronegativity shown as a number. All right, so electronegativity then varies with atomic number, as we saw in the periodic table. And in fact, you can chart this and you see that it increases as you go across a period. Look at lithium to fluoride, very definite. Remember, fluorine has the highest electronegativity. the next row, sodium through chlorine, a little bit less pronounced, but the same general trend. All right, so here's the issue. There is no sharp distinction between a nonpolar covalent bond and a polar covalent, or between polar covalent and ionic. So we had to come up with a set of guidelines to make this judgment. And here are the rules that were developed. So if you have two atoms whose electronegativities differ by less than a half, is considered a covalent or nonpolar compound. So their electronegativities are quite similar. A bond where the atoms' electronegativities differ in the range of 0.5 to 2, this is considered a polar covalent compound. And if the electronegativities differ by more than 2, this is an ionic compound because the high electronegative atom is actually pulling the electron off of the other. All right, so we have a worked example here. Classify the following bonds as nonpolar, polar, or ionic. And so we're looking at the bond in chlorofluoride, cesium bromide, and the carbon-carbon double bond in ethane. And under strategy, they give you those electronegativity values, so you have something to work with. All right, and the solution is this. If you're looking at the chlorofluoride, you only get a difference of 1 from 4 to 3. So this is a polar compound. In cesium bromide, the difference is 2.1. So you have a metal and a nonmetal. So it's ionic, which is what we would expect, being a bond between a metal and a nonmetal. And then in ethane, you have 2 carbons that we're looking at. That's ethylene. And they are actually double bonded. And so that is a purely nonpolar compound. And so here's just a tip to think about. It's always, the subtraction is always done so that you get a positive result so you can readily compare it to the rules. Okay, so now we're going to look at dipole moment, partial charges, and percent ionic character. And so once again, we're looking at this hydrogen fluoride with the blue end and the red end. And so we know this is definitely a polar compound. And we're going to see some charge separation, and we're going to use that delta to show that. And the other way you can do it is with an arrow that points towards the more electronegative compound. It shows this is polar, and we call that a dipole moment, meaning that there is a definite pull towards the one element. All right, now I've included the section here which I went over in class on drawing Lewis structures. So here's the set of rules. And this was the example I did in class about drawing Lewis structures. So we have the chlorate ion, and you'll notice at the bottom it talks about chlorine's electronegativity being 3 and oxygen's being 3.5. So this is not a terribly polar compound, but chlorine still has the lower electronegativity, and that's why it's in the center. And so I've just included these so you can read through this. You have an actual written copy of these slides that I went through. And here's that chart that I showed you comparing the steps that were listed earlier and what these various compounds, all the steps that they would go through. And here's a carbon disulfide example that I did. All right, you can move on to the third video.